Well, we're back. Welcome to the second video in the equilibrium series. So far, we've discussed how to find the equilibrium constant for a homogeneous and a heterogeneous reaction. Now we are going to look at different ways to apply this constant and to solve for equilibrium positions, predict shifts in reactions, and spontaneity. So when looking at the value of an equilibrium constant, there are several things we can predict. As we discussed, an equilibrium constant with a large value suggests that the reaction lies far to the right. An equilibrium constant with a large value also suggests spontaneity. What this does not suggest, however, is how fast the reaction is going. Remember that spontaneity is only that the reaction proceeds forward, but does not have any bearing on the speed of the reaction itself. Remember, rust is spontaneous, but can take years to form. Also, as mentioned, the equilibrium constant can be used to determine the shift in a reaction. When a reaction is not at equilibrium, we can use the law of mass action to determine the reaction quotient, or the current position of the reaction. The reaction quotient, Q, tells us where the reaction is relative to its equilibrium. So for example, if the equilibrium constant for a reaction is 100, and its current position gives us a reaction quotient of 20, we know that the reaction still needs to produce more products before it reaches equilibrium. We determine Q the same way that we determined K. When the law of mass action is applied when a reaction is at equilibrium, it solves for K. When the law of mass action is applied when a reaction is not at equilibrium, it solves for Q and gives the current position of this reaction. To determine which direction a system will shift to reach equilibrium, we compare the current position, or Q, to the equilibrium constant, K. If Q equals K, then our reaction is already at equilibrium. But if Q is greater than K, the reaction is product-heavy compared to the equilibrium position. We can predict then that this reaction will shift to the left towards the reactants to obtain equilibrium. If Q is less than K, the reaction is reactant-heavy compared to its equilibrium position. We can then predict that the reaction will shift right towards products to obtain a higher Q and closer to equilibrium. Let's use Q to determine the shift in these reactions needed to obtain equilibrium. In this practice problem on page 609, we are given current concentrations in a reaction. We need to determine which way the reaction needs to go to reach equilibrium. The first thing we need to do is to write a reaction. The synthesis for ammonia is N2 plus 3H2 yields 2NH3. We will use the law of mass action to determine the current position. The reaction quotient Q equals the concentration of ammonia squared over the concentration of nitrogen gas multiplied by the concentration of hydrogen gas cubed. For part A, you should get a Q of 1.3 times 10 to the 7th. If K is 6.0 times 10 to the negative 2nd, then the current position is very product-heavy. The reaction will need to shift to the left to reach equilibrium. For part B, you should get a Q of 6.01 times 10 to the negative 2nd, which is very close to the value of K. This reaction, part B, is at equilibrium. For part C, you should get a Q of 2.0 times 10 to the negative 3rd, which is lower than our equilibrium constant. This reaction is too reactant-heavy and must produce more products to reach equilibrium. This reaction will shift right towards equilibrium. The last problem we are going to try is practice problem number 8 on page 610. Dinitrogen tetraoxide in its liquid state was used as one of the fuels on the lunar lander for the NASA Apollo missions. In the gas phase, it decomposes to gaseous nitrogen dioxide. Consider an experiment in which gaseous N2O4 was placed in a flask and allowed to reach equilibrium at a temperature where Kp is equal to 0.133. At equilibrium, the pressure of N2O4 was found to be 2.71 atmospheres. Calculate the equilibrium pressure of NO2. So to approach this practice problem, we're going to work backwards from what we've done in the past. Since the reaction is already written for us, we just need to write the equilibrium expression for the law of mass action. This example has gases with pressures, so our equilibrium constant will be Kp rather than Kc. So Kp is going to equal the pressure of NO2 squared over the pressure of N2O4. If Kp equals 0.133, then the pressure of NO2 can be found by plugging in the pressure of N2O4. But don't forget to take the square root of the answer at the end for the pressure of NO2. You should get 0.600 atmospheres. This concludes the second video of the equilibrium series.